Okay, so last time we talked about non-homogeneous equations, and non-homogeneous means when you write down the differential equation, you put all the derivatives y and y itself on one side on the left, and everything else on the right. Non-homogeneous means the right-hand side is not zero. If the right-hand side is zero, that's called a homogeneous equation. So to solve a non-homogeneous differential equation in higher order, we're talking about linear equations here. We need to do it in two steps. First, we need to find the general solution for the associated homogeneous equation. That means you just throw away the part on the right side of the equation so that it's zero, and then you solve that equation and find the general solution to this equation. And then the second step will find the one particular solution to the non-homogeneous equation. Okay, so you come back to the original non-homogeneous equation and try to find the one particular solution. And then you just add the first part, the general solution for the homogeneous equation, and the particular solution you'll find for the non-homogeneous equation, and that will give you the solution to the differential equation. All right. So let's just do one example. Verify that the given two-parameter family of functions is the general solution of the non-homogeneous differential equation on the indicated interval. So again, we're not trying to solve the non-homogeneous equation. We have not talked about even how to solve a homogeneous differential equation at this point. So we just want to verify. So the solution is given and we just need to verify it. All right. The equation we have is y double prime minus 7y prime plus 10y equals 24e to the x. And the solution given in the problem is y equals c1 e to the 2x plus c2 e to the 5x plus 6 times e to the x. So we need to verify this is indeed the solution to the differential equation, and this solution is valid from negative infinity to positive infinity of x. That means for all values of x. All right. So we need to do two things actually. We need to check that the part of c1 e to 2x plus c2 e to 5x is a solution to the associated homogeneous differential equation. And we also need to verify that 6e to the x is a particular solution to the non-homogeneous equation. Okay. And the first part is pretty straightforward. And I think we did a similar problems that list before, maybe the exact problem in one example before. What do you do? You just need to plug in e to the 2x and e to the 5x for y into the equation and make sure the left-hand side gets 0. So, for example, if you plug in e to the 2x to the left-hand side of the equation, you take the second derivative of the function and put in the first term and minus 7 times the first derivative of e to 2x plus 10 times e to 2x. Okay, and that should give you 0. I think we did it last time actually. And similarly, plug in e to 5x to the equation on the left side, you're going to get 0 also. So that essentially tells you that e to 2x and e to 5x are both solutions to the associated homogeneous equation. And then you can easily check the Roskin of those two functions, e to 2x and e to the 5x, and you'll find out that the Roskin will never be 0. So that means the two functions are linearly independent. So according to the theorem we learned before, then you just need to take the linear combination of the two functions, and that will give you the general solution of the associated homogeneous equation. So that's the part of C1 e to 2x and C to the 5 e to 5x. All right. So we already did that before, so we're not going to repeat it here. So the only thing left in the problem is just to check 6e to the x is a particular solution to the non-homogeneous equation. Okay. So what you do is just plug in 6e to the x for y in the equation, and the equation should hold. So when you do that, because the derivative of e to the x is the e to the x itself. So obviously, the first derivative and the second derivative of this function we call yp, which is 6e to the x, is also e to the x. All right. So when you plug that into the differential equation on the left side, we get 6 times e to the x minus 7 times 6e to the x plus 10 times 6e to the x. So 7 times 6 is 42, and 10 times 6 is 60. So you're going to get a 6e to the x minus 42e to the x plus 60e to the x. And if you just combine them, you get a 24e to the x, which is exactly the right-hand side of the equation. So that means 6e to the x is indeed a solution to the differential equation, and it is a particular solution. Okay. So by the theorem, the general solution of the original non-homogeneous linear differential equation will be C1y1 plus C2y2 plus yp, which is C1 e to the 2x plus C2 e to the 5x plus 6 e to the x. All right. So I guess this is not very difficult. Everything looks straightforward. Any questions for this example before we go to the next page? Okay, so no question, then we'll just go to the last slide for this section. Okay. So the last theme in here is still about non-homogeneous differential equations. We're talking about linear differential equations. So again, differential equation in the standard form are written as anx times dny over dxn plus a minus 1x times dn minus 1y over dnx minus 1 plus everything down to a 1x times dy dx plus a 0x times y equal to grx. Okay, so so this time we have a bunch of differential equations. This grx is just a family of functions. I is the index. Okay, so for example, we can have k equations, k differential equations. Each equation will have the same part on the left, but on the right hand side we have different functions, gi, which we call them g1, g2, down to gk of x. Okay, so there are k differential equations, and suppose we already find one particular solution for each of those equations, and we call this particular differential equation, particular solution to the corresponding differential equation yp1, yp2 up to ypk. All right. So these are k particular solution of the non-homogeneous nth-order differential equation on the interval I, corresponding in turn to k distinct functions g1, g2, and to gk. Okay. So that means ypi denotes a particular solution of the corresponding differential equation. Just read in here. So then if we want to find a particular solution of the non-homogeneous equation with the right hand side the sum of all those functions of g's. Okay, so you just need to add all those particular solutions, yp1, yp2 up to ypk. Okay, so that will give you a particular solution of the differential equation, at the bottom. And then from that, we can, find a solution for the differential equation in general. Okay, so what's the point? The point is, if you cannot find a particular solution to a differential equation, then you can try to break up the right-hand side, into several parts. I suppose the differential equation has already been written in standard form. And then you find one particular solution for each part of the right-hand side. And then just add those particular solutions together, then you find the particular solution to the original differential equation. Okay, so that's again a version of superposition principle, right? Okay, let's just do one example. Okay, so okay, again, we're not trying to solve the differential equation. We're going to discuss in the next section, but we just verify the solutions are correct for the differential equation. So we verify that yp1 equals -4x squared is a particular solution of the differential equation y double prime minus 3y prime plus 4y equals -16x squared plus 24x minus 8. Okay, so that's one differential equation and one particular solution. And then we need to verify that yp2, which is e to 2x, is a particular solution of y double prime minus 3y prime plus 4y equal to 2 times e to 2x. And then we need to verify that yp3, which is the x e to the x, is a particular solution of y double prime minus 3y prime plus 4y equal to 2x e to the x minus e to the x. Okay. So we have three differential equations and three particular solutions corresponding to each one. But note that the left-hand side of the differential equation is always the same: y double prime minus 3y prime plus 4y, namely. But to verify, each of those yp is a particular solution of of a differential equation, you just plug in, those YPs into the differential equation and see if the equation holds. So, for example, in the first part, YP1 equals negative 4x squared. So if you take the derivative of YP1, you get negative 8x, and if you take the second derivative, you get negative 8. So that's pretty straight if you use the power rule. So plug those into the different equation on the left side. So we got the, y double prime minus 3y prime plus 4y equals negative 8 minus 3 times negative 8x plus 4 times negative 4x squared. And if you multiply all those terms and rearranging the terms in descending powers, you're going to get negative 16x squared plus 24x minus 8. 4 times negative 4 is negative 16, and negative 3 times negative 8 is positive 24. So this is indeed the right-hand side of the first differential equation. Okay. So that's the first equation, and you can do a similar thing for the second equation, where YP2 is 2e to 2x. So if you take the derivative, I'm sorry, YP2 is e to 2x. If you take the derivative of YP2, you are going to get the e to 2x itself times the derivative of 2x. Remember to use the what rule is it called? Chain rule, right? So the derivative of 2x is 2. So the derivative of YP2 is just 2 times e to 2x. And if you take the derivative again one more time, then you're going to get another 2, when you take the derivative e to 2x. So 2 times 2 will be 4. So that will be 4 times e to 2x, all right? So plug those into the second equation on the left-hand side. You're going to get 4e to 2x minus 3 times 2 times e to 2x plus 4 times e to 2x, and 3 times 2 is 6. So if we combine the 3 terms, you're going to get the 2 times e to 2x, which is exactly the right-hand side of the second equation. So that means YP2 is a particular solution to the differential equation. All right. And for the third one, YP3 equals the x times e to the x. So this time, you have to use the product rule when you take the derivative of this is YP3. So the product rule says if you have a function which is a product of two other functions, then you have to use the product rule. And this is the exact case in here. The two functions in YP3 is actually x and e to the x. So then you just take the derivative of the first function times the second function plus the first function times the derivative of the second function. Okay. So that's why we get the x prime times e to the x plus x times e to the x prime. Again, x prime is just 1 and e to the x prime is just e to the x. So at the end, we get the 1 times e to the x, which is e to the x plus x times e to the x. All right. So that's the first derivative of YP3. If you take the derivative again, you get the second derivative. So now you have two terms, e to the x and x plus e to the x plus x times e to the x. So you just take the derivative of each part. The derivative of the first part is pretty straightforward. The e to the x prime is just e to the x. And the derivative of x e to the x, we already did that when we did the YP3 prime. And that's just the result on the previous line, which is e to the x plus x times e to the x. So we just combine the e to the x, we got 2 times e to the x, and add x e to the x. So that's YP3 double prime. So plug in those YP prime, YP3 prime, YP3 double prime into the equation on the left side. We get 2 times e to the x plus x times e to the x minus 3 times e to the x plus x times e to the x plus 4x e to the x. So you can distribute the -3 in the second part to get the -3 to the x minus 3x e to the x, and then combine like terms. Basically, you can combine x to the e to the x and -3x e to the x and 4x e to the x to get 2x e to the x and 2 e to the x minus 3 e to the x just give you a negative e to the x. So we get 2x e to the x minus e to the x, which is exactly the right-hand side of the third equation. So that verifies that YP3 is indeed the particular solution of the third equation. So then if you add the right-hand side of those three equations, remember the left-hand side is always the same for all those three equations. So if you add the right-hand side of the three different equations, then you're going to get the -4x squared. Oh, no, not negative, but the -16x squared plus 24x minus 8 plus 2e to the 2x plus 2x e to the x minus e to the x. Okay. And you still keep the left side the same, y dot prime minus 3y prime plus 4y. So you get another different equation. So to find the particular solution of this equation, you just need to add all the particular solutions for the previous differential equations, which are -4x squared, e to 2x, and x e to the x. So that will be a particular solution of the last non-homogeneous linear differential equation. All right. So that's just what I just said. We have different functions on the right-hand side of this last equation. Then we can break up the right-hand side in 3 different parts, and for each part, we just find the particular solution and add those particular solutions together to get one particular solution to the differential equation. All right. So this is the end of this section. Any questions?